Okay, number 4. This problem, super important for the test. You'll have one like this and know that it's going to be worth a lot of points. So you want to make sure that you have everything written out properly. So it says find the area that is common. The area that is common. That just means where they overlap between the two polar graphs. So you want to make sure your calculator's in polar mode. And I'm going to graph r equals 1. That's just going to be a circle with radius 1. And then we've got the graph 1 plus cosine of 2 theta. Okay, now I set my window up. Now remember, we're graphing in degrees, computing in radians. So I set my window up in degree mode, so it's going from 0 to 360. When I graph it, clearly I get something super small, so I'm just going to change my window here so I can have a little bit better look on it. Much better. So we're looking for the area that they have in common. So if I were to just sketch this out here, I've got a circle, and then I've got 2 other circles in here. Okay, what we're looking for is we're looking for all of this area that they have in common. But what's going to really help me do this is that as long as I recognize symmetry that's happening here. And what we can see is that this area that they have in common can be broken up into 4 equal parts. And so what we want to do is we want to focus in on one of those parts, and I always recommend focusing in on whatever in quadrant 1. So I'm going to draw kind of a close-up of this. Okay, so what we have here is we have the circle, which is the r equals 1. That's coming up like this. So this is our circle, r equals 1. Then we have this other function, y, we're 1 plus cosine of 2 theta. I'll do that in a different color. That's coming up here. So that's going to be r equals 1 plus cosine of 2 theta. Now what I need to find is I need to figure out what the radial lines are at these intersection points. So I need to find this radial line, and whatever this one ends up being. To do that, I need to trace the 2 functions separately. So I'm going to hit the trace button, and notice I'm on the circle, starts at 0, and I'm going to arrow over till I get to the intersection point between these 2. Looks like I'm there at pi over 4. So I'm just going to label this as theta equals pi over 4, and this is theta equals 0. That's going to give me this area of the kind of the sector that gets created between the origin and that circle. So I'm going to write an integral up for that part. I'm going to do the integral from 0 to pi over 4 of 1 squared d theta. And then I'm going to put the 1/2 in front. To that, we need to add what's happening to this other part. So I've got the 1/2 times the integral of whatever these radial lines are here for that. We can't assume that this point has the same radial line for both parts. So I'm going to go back to my graph. I'm going to arrow to the other function. Turns out that it is the same radial value. It's still 45 at that point. But now I've got to carry this back to the origin. So I'm going to arrow over to the origin, which is at 90 degrees, which is pi over 2. And I'll mark my graph here. So this is theta equals pi over 2. And we have theta equals pi over 4. So the endpoints of integration for this will look like that. And I'll get the 1 plus cosine of 2 theta. All that gets squared d theta. And then since this is just one chunk out of 4 chunks that we need, I need to make sure that I multiply all of this by 4. Could also just multiply by 2, it would be the same thing. Careful plugging this in, make sure you compute it in radians, but the answer will be 1.927.